The concept of a bullet that can steer itself to a target sounds like science fiction, yet this is rapidly becoming a reality. Military technology has always sought ways to improve accuracy and effectiveness. For centuries, bullets have been passive projectiles. Once fired, their path was determined by physics and the shooter's skill. Now, that is changing. The Defense Advanced Research Projects Agency, or DARPA, is at the forefront of this revolution. They are developing ammunition that can adjust its course mid-flight. This marks a significant moment in the history of firearms. The age of smart bullets is dawning, promising to reshape combat. This shift from dumb to smart projectiles is a monumental engineering challenge. Imagine packing complex guidance systems into something as small as a .50 caliber round. These systems need sensors, processors, and control mechanisms. All these components must withstand the extreme forces of being fired from a gun. For many years, guided technology was reserved for larger munitions like missiles and bombs. Bringing this capability down to the level of a rifle bullet is a huge step. It represents a convergence of miniaturization and advanced computing power. This innovation could fundamentally alter marksmanship. The implications of self-guided bullets are far-reaching. Primarily, they promise a dramatic increase in accuracy, especially over long distances. This could be vital in difficult conditions, such as high winds or when engaging moving targets. The role of the sniper, already highly specialized, could be transformed. Furthermore, the ability to hit targets with greater certainty might even reduce the number of shots needed. This would mean less ammunition expended and potentially fewer unintended casualties. This is not a distant dream. The technology is tangible and undergoing rigorous testing. The future of precision engagement is arriving faster than many expected. This essay will explore the fascinating world of DARPA's self-guided bullet technology. We will delve into the specifics of how these advanced projectiles work. We will examine the intricate systems that allow them to navigate and correct their path. The benefits they offer in terms of accuracy and operational effectiveness will be discussed. However, no new technology, especially in weaponry, comes without questions. Therefore, we will also address the potential concerns and ethical issues that arise. Finally, we will look towards the future, considering how this technology might evolve and its broader impact. DARPA's program for self-guided bullets is known as Exacto. This stands for Extreme Accuracy Tasked Ordnance. The name itself clearly states the program's ambitious goal. Exacto was initiated to revolutionize rifle accuracy and range. It specifically aims to help snipers engage targets more effectively. This is especially true in challenging conditions where traditional bullets might miss. Factors like wind, dust, and target movement can significantly affect a bullet's trajectory. The Exacto program seeks to overcome these limitations. It is not just an incremental improvement, it is a leap in ballistic technology. The primary objective of the Exacto program is to give shooters a much higher probability of hitting their target. This is particularly focused on the first shot. In many combat scenarios, especially for snipers, the first shot is critical. Missing can alert the target or reveal the sniper's position. Exacto bullets are designed to compensate for unexpected factors during flight. DARPA has conducted live-fire tests demonstrating this capability. These tests have shown the bullets making significant in-flight corrections. Even novice shooters using the system have been able to hit moving and evading targets. Early demonstrations of the Exacto system were impressive. Videos released by DARPA showed the .50 caliber smart bullets maneuvering to hit their mark. In some tests, the bullets appeared to swerve and change direction visibly. This was a clear indication that the internal guidance system was actively working. The system typically involves a laser designator to mark the target. The bullet then homes in on this laser spot. This technology allows for engagement of targets that would be extremely difficult, if not impossible, with conventional rounds. The success of these demonstrations has proven the viability of the concept. The Exacto program represents a paradigm shift from traditional ballistics. For centuries, ballistics has been about understanding and predicting the flight of unguided projectiles. Shooters have had to master complex calculations. They account for wind, distance, bullet drop, and even the Earth's rotation. Exacto aims to embed much of this skill into the bullet itself. This doesn't necessarily make the sniper obsolete. Instead, it provides them with a vastly superior tool. It allows them to focus more on tactics and target selection, knowing their projectile has a higher chance of impact. This shift redefines what is possible in long-range shooting. Self-guided bullets, like those developed under the X-Acto program, rely on sophisticated miniaturized technology. The key component is an optical sensor located in the nose of the bullet. This sensor is designed to detect a laser beam. A spotter or the shooter themselves uses a laser designator to paint the target. The bullet's sensor then seeks out this specific laser light. This method is similar to how larger guided missiles often work, but on a much smaller scale. The challenge lies in making these sensors robust enough to survive the gun's blast. They also need to be sensitive enough for long-range engagements. Once the optical sensor detects the laser spot on the target, a real-time processing system takes over. This onboard brain constantly calculates the bullet's current trajectory. It compares this path to the location of the laser spot. If there is a deviation, the processor determines the necessary corrections. This happens many times per second during the bullet's flight. The algorithms for these calculations must be incredibly efficient. They need to make decisions in fractions of a second. The miniaturization of processing power has been crucial to making this possible within the tiny confines of a bullet. To alter its trajectory, the bullet needs an actuation mechanism. The X-Acto system reportedly uses tiny fins or aerodynamic surfaces. These fins can make minute adjustments to the bullet's flight path. When the onboard processor decides a correction is needed, it commands these actuators. The fins then steer the bullet, nudging it back towards the target. Think of them as very small rudders or wings. The engineering precision required to manufacture and control these tiny moving parts is extraordinary. They must be strong, responsive, and reliable throughout the bullet's journey to the target. The entire system works as a closed feedback loop. The sensor sees the target or laser spot. The processor analyzes the bullet's path relative to the target. The actuators make corrections. The sensor then re-evaluates the new path and the process repeats. This continuous feedback and adjustment allow the bullet to compensate for various disturbances. It can counter wind gusts, air pockets, or even slight movements of the target. This is what gives the self-guided bullet its smart capability. It is an active participant in its journey, not just a passive projectile. This active guidance is the core of its revolutionary potential. The fundamental goal driving the development of self-guided bullets is achieving unprecedented precision. Military planners and soldiers always seek ways to hit targets more accurately. This is not just about effectiveness, it can also be about resource management and safety. A bullet that rarely misses its intended mark is a powerful tool. DARPA's X-Acto program aims to provide this level of precision even to shooters who may not have extensive training. The idea is to significantly increase the first shot hit probability. This means more targets neutralized with fewer bullets fired. Such capability can be a decisive factor in engagements. One of the major challenges in long-range shooting is overcoming environmental factors. Wind is a notorious enemy of snipers. A sudden gust or a misjudged crosswind can send a bullet far off course. Rain, dust, and fog can also obscure targets or affect the bullet's flight. Self-guided bullets are designed to mitigate these issues. By continuously adjusting their trajectory, they can compensate for these atmospheric disturbances in real time. This allows for accurate shots in conditions that would make conventional shooting extremely difficult or impossible. The bullet effectively fights the environment to stay on target. Engaging moving targets at long distances is another significant challenge that self-guided bullets address. With traditional ammunition, the shooter must lead the target. This means aiming ahead of the target's path, predicting where it will be when the bullet arrives. This requires immense skill and is prone to error. A self-guided bullet, especially one locked onto a laser spot, can follow a moving target. As the target moves, the laser spot moves with it. The bullet's guidance system continuously updates its path to intercept the moving point. This dramatically increases the chances of hitting agile or evading targets. Ultimately, the core objective is to reduce missed shots. Every missed shot in a combat situation carries consequences. It can mean a failed mission, an alerted enemy, or a risk to friendly forces. By improving the probability of a hit, self-guided bullets aim to make each shot count. This increased reliability can change battlefield dynamics. It ensures that when a shot is taken, it has the highest possible chance of achieving its intended effect. This pursuit of near-perfect accuracy is what makes this technology so compelling for military applications. It promises a new level of certainty in a field often defined by uncertainty. Section 5, reaching further range and efficiency redefined. Self-guided bullet technology has the potential to significantly extend the effective range of sniper systems. While traditional sniper rifles can already reach impressive distances, accuracy diminishes greatly at extreme ranges. Factors like wind and bullet drop become much more pronounced. A self-guided bullet can compensate for these factors throughout its longer flight time. This means that shots previously considered too risky or improbable could become viable. Snipers might be able to engage targets from safer, more distant positions. This extended reach offers a tactical advantage, allowing for greater standoff distances from threats. The guidance system within the bullet also reduces the complex burden on the shooter. Normally, a sniper must perform intricate ballistic calculations. They need to account for distance, elevation, wind speed and direction, temperature, humidity, and even the spin of the earth. While advanced scopes and spotters help, it remains a demanding skill. A self-guided system, particularly one using laser designation, simplifies this. The shooter's main task becomes accurately placing the laser on the target. The bullet then handles much of the complex trajectory correction. This allows shooters to react faster and with more confidence. When comparing self-guided bullets to traditional sniper rounds, it's not just about maximum range, it is also about the probability of a hit at any given range. A conventional bullet might technically be able to travel 2 kilometers. However, the chances of hitting a man-sized target at that distance under field conditions are very low. A self-guided bullet aims to maintain a high probability of hit even at extended ranges. This reliability is a key differentiator. It means that the range at which a target can be consistently hit is substantially increased. This redefines what is considered a practical engagement distance. This enhanced precision and extended effective range also lead to greater efficiency. Fewer missed shots mean less ammunition needs to be carried and expended. This can be critical in long missions or in situations where resupply is difficult. Furthermore, achieving mission objectives with fewer shots can save time and reduce exposure to danger. If a sniper can neutralize a threat with the first shot reliably, the overall mission success rate improves. This efficiency translates into saved resources, potentially saved lives, and more effective military operations. The technology promises to make small arms fire more decisive. Transforming combat with the introduction of self-guided bullets could bring about several significant changes. One of the most immediate advantages is the empowerment of individual soldiers. While initially focused on snipers, this technology could eventually become more widespread. This would provide ordinary soldiers with an enhanced marksmanship capability. Imagine infantry units where every soldier can engage targets with much higher accuracy, even under stress or in poor conditions. This could dramatically increase the lethality and effectiveness of small units. It would mean that soldiers could make more of their shots count, changing the dynamics of firefights. These advanced bullets offer particular benefits in complex modern combat environments. Urban warfare, for example, presents many challenges. Targets may appear briefly, move erratically, or be partially obscured. Self-guided bullets could help soldiers hit these fleeting targets more reliably. In rugged mountainous terrain, wind conditions can be unpredictable and severe. The ability of the bullet to correct its course would be invaluable in such scenarios. This adaptability to diverse and difficult environments makes the technology highly attractive for military forces operating globally. It offers a consistent performance edge regardless of the operational theater. Counter-sniper operations and force protection are other areas where self-guided bullets could play a crucial role. Enemy snipers pose a significant threat to troops. Locating and neutralizing them quickly is vital. Self-guided bullets could enable friendly forces to engage enemy snipers more effectively and from safer distances. Similarly, for protecting bases or convoys, the ability to accurately engage threats at longer ranges can prevent attacks or reduce their impact. This defensive capability is just as important as its offensive potential. It helps to create a more secure environment for deployed personnel. Beyond the physical effects, the psychological impact on adversaries should not be underestimated. Knowing that an enemy possesses ammunition that can actively seek its target can be demoralizing. It creates uncertainty and fear. The perception that cover or evasion tactics are less effective could influence enemy behavior. This psychological dimension is a well-known aspect of warfare. New technologies that offer a distinct advantage often have a deterrent effect or force adversaries to adapt their tactics significantly. Self-guided bullets certainly fall into this category of game-changing military innovations. Beyond the battlefield, self-guided bullet technology also has significant implications for law enforcement and security forces. Specialized police units, such as SWAT teams, could potentially benefit from this enhanced precision. In hostage rescue situations, for instance, the ability to make an incredibly accurate shot is paramount. A self-guided bullet could minimize the risk to hostages by ensuring the projectile hits only the intended target. This could be crucial in high-stress, close-quarters scenarios where a miss could have tragic consequences. The focus here would be on surgical precision to save lives. Border security is another area where this technology might find application. Monitoring long stretches of remote borders can be challenging. Security forces might need to engage threats from significant distances or in difficult terrain. Self-guided bullets could provide border patrol agents with an improved capability to interdict smugglers or other hostile actors. The ability to accurately target individuals or vehicles from afar could enhance the effectiveness of border surveillance and control operations. However, the use of such lethal force in these contexts would require careful consideration of rules of engagement and legal frameworks. The technology could also be adapted for surveillance and reconnaissance purposes. Imagine a small guided projectile equipped not with an explosive, but with a sensor package. It could be fired into an area of interest to gather intelligence quietly. While the current focus is on lethal applications, the underlying guidance technology could be versatile. This opens up possibilities for non-lethal uses as well, such as delivering tracking devices or incapacitating agents with pinpoint accuracy. The core capability of delivering a small payload precisely to a designated point has broad potential. However, the potential proliferation of this technology beyond military and authorized law enforcement is a serious concern. If self-guided bullets become more accessible, or if the technology is replicated by non-state actors, the consequences could be dire. Criminal organizations or terrorist groups equipped with such weapons would pose an even greater threat. The accuracy and range offered by these bullets could make assassinations easier or attacks more devastating. Therefore, strict controls and countermeasures would be essential to prevent misuse. The dual-use nature of this advanced weaponry demands careful management and oversight. The advent of self-guided bullets brings with it a host of ethical questions and concerns. One prominent issue is the potential lowering of the skill threshold required for lethal force. Traditionally, marksmanship, especially at long ranges, demands extensive training and skill. If technology makes it easier for less trained individuals to hit targets accurately, it could change who is deployed in such roles. This raises questions about judgment and the value placed on human skill in critical situations. Does making killing easier also make the decision to kill easier? This is a profound question that societies must grapple with. Accountability is another significant ethical challenge. If a self-guided bullet malfunctions and hits an unintended target, who is responsible? Is it the shooter who pulled the trigger? Is it the manufacturer of the bullet, or is it the programmer who wrote the guidance software? In conventional shooting, the responsibility largely rests with the shooter. With smart weapons, the lines of accountability can become blurred. This complexity increases as weapons incorporate more autonomous features. Establishing clear lines of responsibility is crucial for maintaining legal and ethical standards in warfare and security operations. There is also the inherent risk of an arms race in smart weaponry. As one nation develops and fields advanced munitions, like self-guided bullets, other nations will likely follow suit. This could lead to a proliferation of increasingly sophisticated and potentially autonomous weapons. Such an arms race could be destabilizing, creating new tensions and increasing the chances of conflict. The pursuit of technological superiority in weaponry often fuels further development on all sides. This cycle can make the world a more dangerous place, even if the initial intent is defensive. Managing this competitive dynamic is a key challenge for international security. Furthermore, while current self-guided bullets require a human to designate the target, the technology edges closer to autonomous targeting. The fear is that this could eventually lead to killer robots, weapons systems that can select and engage targets without meaningful human control. This raises fundamental moral objections for many. The prospect of machines making life or death decisions on the battlefield is deeply troubling. Discussions around the ethics of autonomous weapons are already underway globally. Self-guided bullets, while not fully autonomous, are a step along a technological path that requires careful ethical navigation. The future development of self-guided bullet technology is likely to focus on several key areas. Further miniaturization is a probable trend. As electronics and sensors become even smaller and more powerful, it might be possible to incorporate guidance into smaller caliber bullets. This could make the technology accessible to a wider range of firearms, beyond just 50 caliber sniper rifles. Cost reduction will also be a critical factor. Currently, these smart bullets are undoubtedly expensive. For widespread adoption, the price per round will need to decrease significantly. This will depend on manufacturing advancements and economies of scale. Integration with advanced sighting systems and artificial intelligence is another avenue for evolution. Future sights might not only designate targets, but also communicate more detailed information to the bullet. AI could assist in target recognition, prioritization, and even predicting target movement with greater accuracy. This could lead to even more effective and smarter projectiles. The synergy between the bullet, the weapon, the sight, and the shooter, or an AI assistant, will create a highly integrated weapons system. This holistic approach will likely define the next generation of precision-guided small arms. Beyond lethal applications, the core technology could be adapted for non-lethal purposes. Imagine guided projectiles that deliver incapacitating agents such as pepper spray or sedatives with extreme precision. This could be valuable for law enforcement in de-escalating dangerous situations without resorting to deadly force. Similarly, guided markers or trackers could be deployed accurately from a distance. The underlying ability to steer a small projectile opens up a range of possibilities beyond simply causing harm. This diversification could see the technology used in crowd control, animal management, or even search and rescue. The long-term impact of self-guided bullets on military doctrine, training, and the very nature of armed conflict will be profound. If accuracy becomes largely a function of technology rather than shooter skill, training regimes will need to adapt. Military tactics might change to leverage this new precision or to counter it. The psychological impact on soldiers, knowing they face such accurate weaponry, will also shape the future battlefield. Ultimately, self-guided bullets are part of a broader trend towards increasingly intelligent and precise weapons. How humanity manages this powerful technology will be a defining challenge of the 21st century.